look for is like, look at the rings and look for the alternating single and double bond rings. You want a 6-membered ring, alternating single and double bonds, and that's either going to be an aromatic or it's going to be a phenol. So do you see one? Okay, so which one is it? Yep, so can you see that? So that's a phenol. Now, once you circle that, then that's like, you don't name anything else in that. So you wouldn't name it as an alcohol, you wouldn't name it as an aromatic. If it's a phenol, then that's all it is. Okay? So then I said the next thing to look for is look for any nitrogens, because nitrogens, if they're all by themselves, look at adjacent carbons. If the adjacent carbon has a double bond oxygen attached to it directly, then that's an amide. If there isn't, then that's an amine. So do you see a nitrogen? On top of that second ring, so that means this would be a, so I look at this carbon and I look at that carbon. Do you see that neither of them have a double bond oxygen? So that means this is an amine. Okay? So then, do you see any other nitrogens? No. So then the last one that you can just automatically check off is what? The sulfur, which makes this a thiol. So see thiol. Doesn't matter if the sulfur has an oxygen or if the sulfur had a nitrogen. If there's a sulfur, it's a thiol. So there's no, that's all that they would be. So that's now named the rings. Notice that middle ring is not an aromatic because it doesn't have an alternating single and double bonds of carbon. It's just a cyclohexane, but it has a nitrogen in there as well. And then, so then the last thing to do is look at oxygens. So can you pick out one of the oxygens and tell me what it is?
The OH off of the second ring is an alcohol.
Yep, can you see that? So see this one? So it's just attached to a carbon. That carbon just has hydrogen on it. There's nothing else on it. So this is an alcohol. And then what about the other one? It's an aldehyde. Good, yeah. So see how that's a carbon with the double bond oxygen and an H. It's always on the end. That's an aldehyde. Okay? All the rest of them are nothing but carbon. So once you've like kind of circled everything else and all the rest are just carbon with single bonds, and you just leave them alone. They're all alkanes. Okay? So those are just some functional group examples. And that goes back from like chapter 4. So then remember this, we were talking about identification of what kind of chemical reactions these are. They're either synthesis, decomposition, single displacement, or double displacement. So what is the first one? So these are either synthesis, decomposition. This is the least favorite pen. It can be, come on. It's like not responding at all. Okay, try it again. And then it's like, yeah, sure. Let me just throw you off with the LCD protector. All right, and so in this one, these are going to either be synthesis, decomposition, single displacement, double displacement. So remember synthesis, there's more reactants and products. Decomposition, more products than reactants. If they're equal, then it's one of the displacement ones. So if they're equal, if it's an element in a compound, it's a single. If it's two compounds, it's a double. So this first one is a what? It's a single displacement. So this one's an SD, single displacement. What about the second one? It's a decomposition, right? So you see that you start off with one reactant and there's two products. So what about this one? So CuO plus H2 makes H2O and Cu. What is that one? Well, so this is an element and that's an element. So if you have a compound plus an element, then it's always single. So it doesn't matter if it's an element and a compound or a compound and an element, no matter how the order is listed, just look at the two reactants. If you have 2 and 2, if one of them is an element and one of them is a compound, then you know it's going to be a single displacement. They have to both be compounds for it to be double. Okay, so what about the next one? So here, see, it's magnesium hydroxide and HCl. So do you see that those are both compounds? That one's a double. Okay? So single, the way you can pick out a single compared to a double is single is always going to be an element in a compound, making a different element in a different compound. What about the next one? Yep. Okay. So this is like one of the ones that we left. So we did this one in the last time, talking about synthesis, double displacement, decomposition, single displacement. So this is the other one, the other example. So KMNO4 forms K2MNO4 and MNO2 and O2. So this is what? Decomposition. This is decomposition because I only have one reactant and I have 3 products. Okay, so it doesn't matter if one thing makes 2. One thing could break down into 10. It's still decomposition. So just think if you start off with a single or fewer reactants. I could even have 2 reactants but make 3 products. That would still be decomposition. So if it's not any equal number of reactants and products, then I know it's synthesis or decomposition. If it's equal numbers, then you look to see are they an element in a compound or 2 compounds. So like this next one, what would this be? That's also another decomposition, right? Because I have one reactant, but I have 3 products. Decomposition. Zinc plus HCl makes H2 and ZnCl2. So notice I have 2 of each. I have 2 reactants and 2 products. So this one is a what? This is a single displacement, okay? If you have an element in a compound and making a different element in a compound, that's single displacement. So the kicker is you can tell it's one of those if you have equal numbers of products and reactants. Whereas if you have SN plus Cl2 makes SnCl3 or Cl4. So notice I have 2 reactants, only 1 product, so this is synthesis. Right, so this is going to be a synthesis reaction. And both of the last 2 are what? They're both doubles. So they're both double displacement. And the way that you can tell, so I have 2 reactants and 2 products. Since they're equal, I know it's a displacement of some type. Since they're both compounds, that makes it a double. Whereas when I have 2 reactants and 2 products up here, but this is an element, and this is a compound. Whereas over here, these are both compounds. So that's really the difference between a single displacement and a double displacement. Single displacement is when an element and a compound swap a partner, but in double displacement, both compounds swap partners. So it's sort of a double swapping that occurs.
And synthesis is when one break down into...
Nope, that's decomposition. So think of that as things breaking down, right? If one makes 2 or one makes 3 or one makes 10, it's decomposing, right? Things breaking down. But if I have 2 makes 1, or 3 makes 1, or 20 makes 1, those are all synthesis, right? So just remember, more reactants is synthesis. More product is decomposition. Okay, so I just did those just so that we could do a review, just to make sure that you're with me on that. But this is where we kind of quit last time, was talking about oxidation and reduction. So in oxidation and reduction, this page is really kind of like these are the 4 examples that you'll see. Okay, so you're going to see these 4 types of examples. The first one is if you're making an ionic compound. A metal plus a nonmetal makes a salt, right? So sodium plus chlorine makes sodium chloride. So in this, the metal is always oxidized because it loses electrons, right? So loss of electrons is oxidation, so that's LEO. So that LEO, loss of electrons, is oxidation. Nonmetals, because they gain electrons, like chlorine becomes a negative ion, it's going to gain electrons, and that is why it's reduced. So remember the little mnemonic for that one is GR. Loss of electrons, LEO. Gain of electrons is reduction, so that's GR. Metals are always oxidized. Doesn't matter what the metal is. So if you look at the periodic table and you see 2 things, your reactants are on opposite sides of the zigzag line, you know the metal gets oxidized, the nonmetal gets reduced. If you have a combustion reaction, so remember in a combustion reaction, that's anything combining with oxygen and making carbon dioxide or in water. It could be plus oxygen makes water and carbon dioxide. It doesn't matter which order the water and carbon dioxide are written. So notice here I have CO2 plus H2O. It could be H2O plus CO2. Just remember either way, if carbon dioxide and water are products, the fuel is always oxidized because the carbon and the hydrogen in the fuel add oxygen to them. So carbon with hydrogen becomes CO2 and H2O. And that means that the oxygen is the source of what oxidizes the fuel. So oxygen in a reaction is always reduced. And then the last 2. The last 2 are just where you're doing single displacements. Do you see how those are single displacements? I start with an element in a compound. I end up with a different element in compound. But in these 2, it is only where I have swapping of oxygen or swapping of hydrogen. In example number 3, whichever reactant is the element, if it gains oxygen, do you see how like Y becomes Y with an oxygen? It becomes oxidized. So if the reactant gains oxygen, it gets oxidized. If the reactant X, which starts off with an oxygen, but now on the product side, it's just X all by itself, do you see that X loses its oxygen? If it loses oxygen, it's reduced. So notice that that's different. Loss of electrons is oxidation, but gain of oxygen is oxidation. So it's not like loss of any of these or gain of any of these. The criteria are different for oxygen compared to electrons and hydrogen. So electrons and hydrogen actually follow the same route. So we said up at the top, if something loses electrons, it's oxidized. If it loses hydrogen, it's also oxidized. So if you lose electrons or you lose hydrogen in an oxidation-reduction reaction, that's oxidation. But if you lose oxygen, that's reduction. So that one's where it's different than the norm. So in this last one, if you look, X has H attached, but on the product side, X is all by itself. So you would say in example number 4, X loses its hydrogen. That means it's oxidized. Y starts off without anything, but on the product side, now Y has H attached to it. So Y has gained hydrogen, that's reduction. So loss of electrons, loss of hydrogen, or gain of oxygen, those are all oxidation. And so the exact opposites are reduction. Because if something gets oxidized, something else is always going to get reduced. Because if something loses electrons, something's going to gain it. If something loses hydrogen, something's going to gain it, right? So in these reactions, if you see this swapping of oxygen or hydrogen, especially, I'll just use the single displacement reactions. You can identify oxidation and reduction. Fuel, burning of fuel is an oxidation reduction reaction. Just always remember fuel is always oxidized. And the oxygen in a combustion reaction is always reduced. And then if we have a metal and a non-metal, metals are always oxidized because they lose electrons. Non-metals are always reduced because they're going to gain. So we did a couple of examples here, but I have one more. Oh, well, here's your one more. Okay, 1, 2, 3, 4, 5. So I'll give you a couple of minutes. Now remember, when you do this, one, always find something that's not hydrogen or oxygen, right? Because they're the things get swapped. So look at the reactant, and you're asking yourself what happens. If it's a synthesis like this first one, then I know that it's going to be ionic, because I'm not going to give you any other examples of synthesis unless it's ionic. So if it's ionic, what do I know? What happens to the metal? So the metal, does the metal gain or lose electrons? So this is going to be, you look on the periodic table, so I see that I have magnesium and I have nitrogen. Looking on the periodic table, magnesium's to the left, nitrogen's to the right, so I know it's an ionic compound. And pretty much, if it's an oxidation reduction reaction and it's a synthesis reaction, it's always going to be an ionic compound. So just figure out which is your metal, which is your non-metal. What happens to the metal? Which means that it is? And then look at the non-metal, identify the non-metal reactant. You know that it is going to gain electrons from the metal, so that means it is. And notice that I always identify the reactants as oxidized or reduced. I don't talk about the product. It's always looking at like, well, what happens to the reactant when it goes through the reaction? The next two are single displacement. Does everybody see that? So the next two, you have an element in a compound making a different element in compound. So if it's single displacement, then you're looking to see which one swapped hydrogen or which one swapped oxygen. And then the last two, they're both synthesis. So it's just a matter of identifying which is the metal, which is the non-metal, and that's oxidized or reduced. So I'll give you a minute to do those. Okay, so in a single displacement, you're looking to see, am I swapping oxygen or swapping hydrogen? So in the first one, what happens to calcium? So it is? So calcium is oxidized. Everybody get that? Okay, so calcium is oxidized because it gains oxygen. So if you look at H2, and then over on the product side, what is it? No, it's just H, right? So see how it's H2O? So the only time you're looking at metals and nonmetals is if it's a synthesis reaction, because then it's an ionic compound. So see the first one? I have a metal and a nonmetal, and I combine. So it's a synthesis reaction. Metal is oxidized, nonmetal is reduced. The second one is a single displacement, so I have 2 and 2. So look at the reactant and look at what happens to it in the reaction. Do you see Ca becomes CaO? So I say, oh, it gains oxygen. If it gains oxygen, that means that it's oxidized. So then if I look at H2O, it loses its oxygen and becomes H2. So I see that it is reduced. Because it, H2O, the hydrogen of H2O, loses its oxygen. But now what about when you look at the second one? What happens to chlorine? Chlorine gains hydrogen. See how chlorine becomes HCl? So if I look here and I look across, I see that chlorine gains hydrogen. But if it gains hydrogen, what is that? Nope. See, this one's the one that's sort of odd. If you gain oxygen, it's oxidation. But if you lose electrons or lose hydrogen, that's oxidation. Okay, all of those. So they're not exactly the same. So this is reduced. So the rule, if you're oxidized, if you lose electrons or you lose hydrogen, or you gain oxygen. Those are all the criteria for oxidation. Loss of electrons, loss of hydrogen, or gain of oxygen. So notice they're not all the same. So most people think like, oh, it's loss of any of them, it's oxidation. Not with oxygen. It is loss of electrons and loss of hydrogen. So if I look at H2O, do you see here then H2O, the hydrogen loses, or sorry, the oxygen loses its hydrogen? That means that it is oxidized. And it's always the reactant. And in single displacement, you're just looking to see what gets swapped. Is oxygen getting swapped or is hydrogen getting swapped? It's going to be one or the other. So Sn plus Cl. So Sn is a what? On the periodic table? It's a metal. So I know it is oxidized. And chlorine is a non-metal, so I know that it is. Iron is a metal, so I know that it is also oxidized. Oxygen, anytime oxygen is a reactant, it is always reduced. I mean, it is here because it's a non-metal. But oxygen, like always, gives its oxygen away. It doesn't ever stay combined. So in that synthesis, if oxygen is involved in the combustion reaction, it's also going to be reduced as well. Okay? But look, one, identify the kind of reactant. If it's a synthesis reaction, the only examples you'll have are forming ionic compounds. If it's a single displacement, then just look at the non-hydrogen, non-oxygen atoms that are reactants and see what happens. Are they swapping hydrogen or are they swapping oxygen in the reaction? And then go by that rule. If you lose electrons or lose hydrogen, that's oxidation. If you gain oxygen, that's oxidation. So those criteria. So reduction's the exact opposite. So reduction, you gain electrons, you gain hydrogen, or you lose oxygen. Because it's like the opposite of oxidation. Okay, so we'll try and do another one next time. So now, this last section really leads into the whole idea of lipids, but it's talking about common reactions that form or break molecules apart, and we're really talking about these organic molecules. So here we're talking about carbohydrates, talking about lipids, talking about proteins, and the way that the building blocks are linked together in a synthesis reaction, or the way that they're broken apart, they use the term condensation or hydrolysis. So when you think of condensation on your windows, what forms? Water, right? That's when your windows fog up, condensation. So whenever you think condensation, think water is a product. Right? So the bathroom mirror steaming up in a hot shower, condensation, because the mirror is cool. So when that warm steam hits that cool mirror, it condenses and forms little droplets of water. But hydrolysis, lysis means to break. So hydrolysis is like breaking with water. So that means water is a reactant. So these are kind of like the opposites of each other. So if I go in this direction, I will remove a hydrogen from one molecule and an alcohol group from the other and form a link between these two molecules. So if you look at it, do you see the red? So on one side, I have an alcohol group. And it could just be that it was an alcohol. It could be that it was a carboxylic acid, but I'm going to have that OH group hanging off of a molecule. And then on the other side, I have another alcohol group, but I'm just going to pull the hydrogen off. And it forms this link. So when I have this link, what is that? Look on your functional group handout. When I have carbon with an oxygen as part of the chain, that's a ether. So this is an ether. There are some examples of this where you actually make an ester. So look on your functional group page. So remember that if I have it like this, do you see that that's an ester? So there are some circumstances where that link that is formed could be an ether or an ester. That's condensation. Two pieces are being linked together by pulling water out. So this side and this side, remember that they have to have their bonds to be stable. So removing water is condensation. So notice that water is a product in this reaction, if I'm going left to right. But this is a reversible reaction, so I can also go from right to left. So I can take the exact same big molecule, and now I can do hydrolysis. So that means that I actually use the water molecule to split the bigger molecule into two smaller pieces. So notice there, water is a reactant. So I'm actually going in reverse. So which one do you think requires more energy? Condensation or hydrolysis? So think about which one looks more like synthesis? Which one's making things bigger, like building things together? So you see condensation, when I go left to right, that is like building muscle, building protein, making things grow, making larger structures. Condensation is typically a lot more like a synthesis reaction. It's a lot more energy demanding. But you see hydrolysis is like taking something and split it into two pieces, using water to help split. Remember I told you when you break bonds that helps to release energy. So hydrolysis is more like digestion. Condensation is more of your synthesis, building up type of reactions. So example, this adenosine triphosphate forming adenosine diphosphate plus energy is that, notice when I go from left to right in this one, see how I have water is a reactant in this? So that's a hydrolysis reaction. So hydrolysis reactions, not in every single case, but in most cases, you end up releasing energy. So it's kind of like a decomposition. We're breaking bonds. Help to release energy. And remember, this ATP is this universal energy molecule that your cell makes. So if your cell breaks down nutrients like glucose, like proteins, like fats, that energy that it gets can actually be used to power the reverse. So we can power the reaction of condensation. So we can go the exact opposite direction. And in doing this, we can take this nutrient energy and use it to build ATP. So that is like what your cells do to try and generate ATP, is they break down nutrients and use it to be able to build that energy molecule, just so that you can do hydrolysis and then be able to do whatever the cell has to do, whether it needs to make certain proteins or if it has to package materials in a certain way. All of that work of the cell is typically your hydrolysis. So it helps to do cell work. Remember, that's energy, the ability to do work. So hydrolysis, in a large extent, releases that energy to help power what's going on in the cell. Whereas condensation is is how you break down nutrients to trap that energy as ATP. We basically do this back and forth all the time. Your cell's constantly trying to build up a supply of ATP, but then at the same time, it's constantly using it to be able to power the condensation reactions that you need to do. Okay. All right, so then this leads us really to our first nutrient group. So we're going to talk about lipids or fats, oils. We're going to talk about carbohydrates in the next chapter, and then we're going to talk about protein. So those are kind of the three. So this first one, these are called lipids. So whenever you think of lipids, just think about anything that is described as being a fat or being an oil. And whether they're a fat or an oil really just depends on whether or not there's any double bonds in the molecule. So if you have one double bond between carbon atoms, they call that monounsaturated. If you have more than one, then you will typically have a double bond, single, then another single, then another double. This would be called polyunsaturated. So you can actually have a fat that has one double bond, two double bonds, three double bonds. In fact, there's 4 is kind of the highest, but 2 and 3 is much more normal, but they call it polyunsaturated. Remember, poly means many. So more than one is poly. If there's only one double bond in the carbon chain, they call it monounsaturated. If they're all single carbon-to-carbon bonds, they call it saturated. So saturated has no double bonds, so that means that the carbon chain is nothing but single carbon-to-carbon bonds. Remember, up, down, left, right. So they really consider lipids as a category a hydrocarbon. They do actually have 2 oxygens on them, but in comparison to all the carbons, lipids are typically chains of 12 to 22 carbon atoms in one long chain. So this is 4, 5, 6, 7, 8, 9, 10, 11, and then at the end. This is the shortest, just because it gets like... So notice at the end there's 2 oxygens. It's a carboxylic acid. That's that functional group on the far end. And so you'd be like, oh, that part's polar. Well, but then you look at the fact that there's that in this one there's 12 carbons. That's a whole lot more than oxygens. Remember I told you that polarity, determining polarity, if the molecule's small, then that really works. Like H2O, oh, there's an oxygen, it's polar. NH3, oh, there's a nitrogen, it's polar. But here, yes, there's 2 oxygens on that end, but there's a long chain of carbon. This could be 22 carbons in a chain. So they just get bigger from there. This one's a relatively small one. But because of that, this really has much more of a nonpolar effect. And this has much less of an effect because there's so many carbons. They're not even close to equal. There's only 2 oxygens and you got 12 carbons or 16 carbons or 18 carbons. That's why fats and oils don't mix with water. That's why fats and oils tend to be nonpolar, because they have these long carbon chains. Now, if I have double bonds in there, I would just add a double bond, decreasing the amount of hydrogens between 2 of the carbons in that chain. In fact, looking at these, this is the first example. So the one that I just drew is lauric acid. You don't have to learn the names of any of these. It's fine. Just looking at them, these are all considered, and this is like marked wrong, these are all saturated. And they call these carbon chains that you find in oils and fats, they call them fatty acids. And the reason is because on the end is a carboxylic acid. So that's where the name comes from. So it's like a fat with the carboxylic acid, which is why they ended up calling them fatty acids. So they just consider that's like kind of the chain itself. So coconut oil has a lot of this one. Then there's nutmeg, palm, some animal fats, peanuts, canola. These are just examples of saturated fatty acids, anywhere from 12 to 22 carbons. So remember, in that zigzag, every corner and every end would be a carbon. So you'd have to go 1, 2, 3, 4, 5, 6, right? All along the zigzag, counting them, and then all the way down at the very end, there's your carboxylic acid. So there's the double bond oxygen and the OH. So all of them, each one of them has a carboxylic acid on the end. So that's where that name comes from. But now if we have unsaturated, so this top two examples are monounsaturated. So notice still zigzag, 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 but notice where you have the double bond. It is always this arrangement. It might be this arrangement, but it's always this arrangement. So remember when I told you that double bonds don't have free rotation, so they get locked in position just like ring structures do. So what kind of stereoisomer is that? Is that cis or trans? So when you look at that double bond, the sort of angle that the lines are coming off of the double bond are both sticking in the same direction. So this would all be cis. So these are all cis. In nature, any unsaturated fatty acids will only have cis double bonds. So remember, trans would look like this. Trans would be like that. So you'd have the double bond, you'd have one angled up and one angled down. So remember, trans is across. So cis, they almost look kind of like a little U kind of shape. Okay, so this, trans, there are none found in nature, which like leads to a big discussion we'll have. So here, so palmitoleic acid, that has 16 carbons. Oleic acid has 18 carbons. Those are monounsaturated because they just have one double bond in the chain. Polyunsaturated have 2, 3, and even as many as 4. And I will tell you that these two, linoleic and alpha linoleic, these are actually considered essential fatty acids. You need to have these in your diet. These are used for building things like membranes. We're going to talk about what lipids are used for in a minute, but these are actually considered essential. Anytime something is essential, it means that you need it in your diet, that you don't make it. But look, you can get this from soybeans, safflower, corn, flaxseed, canola. So you can get this from any kind of vegetable oil. And so most people, even in the course of the day, you eat enough foods that have oils in them that you get plenty. Like there's very few people that are actually like, that don't get enough of these types of oils in their diet compared to like vitamins and compared to some of the amino acids that you have to have. This is rarely a problem. But these have always been considered like actually like good fatty acids. They talk about omega-3s and omega-6 fatty acids, the polyunsaturated. Now, what do you use these for? So whenever you think of lipids, if you think of fats and oils, just think of them as a category of lipids. Biggest thing you use them for is you use them to build membranes. So membranes are the covers that help to enclose and protect the cell. These oils are really important in forming insulators. A good example is myelin. So when until a baby is between 2 and 5 years of age, depending on their weight and size, they tell them not to give them low-fat milk because they actually need the fat. They need whole milk. They need that higher fat content to build myelin. And what does myelin do for a nerve? Why do you need myelin? Come on, A&P people. What does myelin on a nerve fiber do to a nerve impulse? People that have MS, the myelin gets stripped off of nerve fibers, and that causes nerve impulses to go faster or slower? Slower. So myelin, it's almost like, so if you think of a wire, like your wire in your house, right? So the wire, the bare copper wire, it's always got a cover on it, and that's an insulator, so that electricity just goes straight through that wire. With a nerve fiber, nerve fibers are formed, or nerve impulses are formed because of exchanges of sodium and potassium. So sodium moves in, potassium moves out, sodium moves in, potassium moves out. And so it actually has to happen all along that nerve fiber unless there's myelin. Myelin is kind of like a little plastic cover, a wrapping over a section of the nerve fiber, so the nerve impulse can actually skip over that area. Then you have another little section and it'll skip. So this means your nerve impulse can go boink, 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 boink. Okay? Otherwise, it has to like walk down the nerve fiber all along the entire surface. So think of myelin as it covers your nerve so that nerve impulses can go really fast. So if you have a highly myelinated nerve fiber, that's going to send nerve impulses like 100 meters per second, like a football field in a second. If you don't have any myelin, then it knocks it down to about 1 meter per second. Now you think like, okay, that's a meter. That's still really fast, 1/1000. So a nerve impulse can go this fast. But when you're talking about posture muscles, right? So balance muscles, do you want to have responses that take that long? No, because then you like be losing balance and everything. That's what happens with people with multiple sclerosis. So MS strips myelin off of those nerve fibers, so their reaction time is slowed, their fall risk is slowed, their choking risk increases, because swallowing is a huge process of muscles, right? So you chew and you chew, then your tongue pushes food up against the hard palate, pushes it back to the soft palate. Soft palate rises, your throat muscles squeeze and start food down into your esophagus, closing over the opening to the trachea, your windpipe as it goes along. All of that is like coordinated because it's all controlled by nerve stimulus. So this is why it's a huge choking risk. If your nerves don't send those impulses at the right speed to keep everything timed correctly, now you're like half done swallowing and then suddenly like your epiglottis lifts because it wasn't stimulated appropriately. So there's like, my one friend that had MS, like she started walking with a cane, right? Because she just felt like she'd go to lift her foot. She's worse than me. She'd go to lift her foot and like she wouldn't be able to lift it enough. And so like there's a fall risk, like getting up, even stepping up onto a curb. A curb is a risk. And then the same thing, like she stopped going out and eating with us because she would like sit at home, and when she would eat, it would take her a long time to eat because she was slow and deliberate about everything she did when she ate, because she was absolutely terrified about choking to death. Like she didn't like to eat unless somebody else was home, because she wanted to make sure that like there was always somebody around if she was going to be eating. There was no like, casual snack kind of thing. It became this big, huge thing. So myelin, it really just helps to insulate a nerve fiber and speed up how fast nerve impulses go. So that's why they say babies need whole milk, because there's a higher fat content. And that way they can use that to myelinate their little nerves as they're developing and forming those new connections, so they start acting like they have sense, right? Because like a 2-year-old, they like have no sense whatsoever at all. Well, you just blame it on the lack of myelin. They don't have the ability to process yet. So you've got to make sure that they get enough fatty acids in their diet so they can make this myelin. Think about protection, coverings on internal organs. So having a fatty cover can help in protecting. So like typically if you look at like where the kidneys are, you'll find like this fatty cushion around the outside of the kidneys. And so the kidneys are embedded in the back wall of your abdominal pelvic cavity, but they have this little fatty cover, and that kind of protects them. Like I just think about like those, the ultimate fighting guys and the like boxers and stuff like that, like beating each other to a pulp. And I'm always like, oh, their liver, oh, their kidney. Like, that's like when I watch, that's all I can think about is their poor little internal organs are getting bruised. And I'm like, I'm sure they're probably peeing blood that night. That's just awful. But that's actually having that little fatty layer in around those deep organs gives them a cushion. Okay, so it's a little more protective. We store fat underneath the skin in subcutaneous layers. That helps for body temperature regulation. And then the last, this and this can really kind of like play these big sort of roles, like what does your fatty acids, what do they need to be used for? But you can also burn these for energy. You can break down fatty acids and generate lots of energy because remember that they make 9 calories per gram. So you can actually make more energy from these lipids than you can from carbohydrates and proteins, which only have 4. But your body really likes to store them because you can store them without water. So you can pack fatty acids into a fat cell and there's no water there. So that gets very compact storage compared to the others that we're going to talk to that are more polar, like carbohydrates. Carbohydrates like water. So when carbohydrates get stored, they're stored with water. But fats can be stored in a fat cell and they don't have to be stored with water because they're non-polar. Right? So they wouldn't mix with water even if there was water there. So fat cells are typically 98% droplets of fatty acids. So you just pack all of these fatty acids into the fat cells, and if fat cells get too big, they will divide, but they never actually decrease in number. So you can swell your fat cells up and they'll divide, but you can shrink them, but they're still there. They're just smaller. Yeah, I know, that's great, eh? All right, so these are all things. This is why you need fats and oils in your diet. So you really do, it's like the low-fat diet, you still need them. When you think about things like, oh, if you eat olive oil, you're not just eating one type of fatty acid. When you eat olive oil, it's actually a mixture of saturated, remember that this is all single bonds. Monounsaturated means that in the long carbon chain, we only have one double bond. Or polyunsaturated, which is going to have more than one double bond. But notice that olive oil is a blend of all 3. But the biggest majority is the monounsaturated. So out of all the ones that are listed, it's really the one that has the highest amount of monounsaturated. Sunflower oil and soybean oil, corn oil as well, they have a lot of polyunsaturated. So canola oil, when you look at it, you're like, you know, it's really pretty close to olive oil. Okay? They're pretty similar in amounts. Canola oil really didn't start being used like aggressively as an oil for eating until like the 1950s, 1960s. So prior to that, canola oil was oftentimes used as a lubricant for machinery. Well, but that's because that's a characteristic of fats and oils, right? They're greasy, they're slick, they're slippery. So they actually used to use canola oil as like a lubricant for large machines, especially during the World Wars. World War I, World War II, like you were building a lot of tanks, a lot of equipment, a lot of ammunitions, and a lot of that type of materials. And so canola oil was put in a lot of machines as a normal lubricant. So when you look at all of these, which ones are animal products? Butter. So this one's an animal, and lard. Yep. Right, so lard comes from rendering, it comes from pig skin. So if you take pig skin and you boil it, the stuff that comes off, that's lard. I know, it makes really good biscuits. Not gonna lie. All right, and then butter. So butter, you know, comes from the cream of milk. You chill milk, the cream comes to the top, you skim it off, and then they churn it until it becomes this nice creamy butter, okay? Right, so they're both animal products. So they have a very high percentage of what? Compared to the others that you see at the bottom. Yep, they have high saturated. So they have a much higher saturated, which means all single carbon to carbon to carbon to carbon to carbon, right? 12 to 24 or 22. Saturated, think all single bonds between carbon. Now, coconut oil and palm. Coconut oil. Does anybody have coconut oil? Anybody use coconut oil at home? Okay, well, what does it look like? Is it a liquid or is it a solid? It's a solid. This coconut oil and palm, they're called tropical oils. So they grow on the coconut tree and on palm trees. And those are typically found closer to the equator. So they're found in tropical areas. And the average temperature of areas around the equator are higher or lower than around here? Higher. So that is why a coconut oil, if you got coconut oil where it was grown, it would be a liquid because it's warm. If you warm coconut oil up to about 80 degrees, it liquefies, okay? So in our 70, 75 degree house, it's not. It's going to be a solid. Same thing with palm. If you can get palm up to about 82, 83 degrees Fahrenheit, palm oil will liquefy. So they come from tropical regions. So they're plant oils, but they have a similar characteristic to animal fat content because they live in or grow in tropical regions. Whereas all these you can grow in North Carolina. Okay? Soybean, olive, sunflower, corn, canola. I'm not sure what a canola plant looks like. I really don't know what it looks like. I don't know if it's I don't know what it's a combination of. I really need to look and find out like what that plant actually looks like. So I know, like you've seen soybean fields around here, right? Okay, so we don't really have a whole lot of olive trees, but olive trees can be grown in areas in North America, typically more closer to like California, Texas, those areas. But corn, you can definitely think of, everybody's seen like sunflowers growing around here. So these are all plant. And more like, not tropical plants, they're more temperate plants. And you notice that they have a much more unsaturated. So they have at least one or more double bond carbon in the chain. So fats and oils typically are not one kind of fatty acid or another. They're typically a combination. But now if you have more saturated fatty acids, then that means you have more single bond long carbon chains. Like this first example, a saturated fatty acid, like an animal fat or your palm or coconut oil, because it's all single bonds, remember when you were starting to build these in lab, like you end up making this molecule that just has a long zigzag, okay? I always think of those as those are like knives in your utensil drawer. Like when you throw knives in the drawer, do they all fit in, right? Are they all straight? So they all fit in tightly, so they pack in real well. That's how saturated fatty acids are because they have all single bonds. The chain pack in really tight, so I can end up with this zigzag and this zigzag and this zigzag and this zigzag. They all pack in like knives in a drawer. And they can pack in tight enough, they can become solid. Because remember, solid things have to have a really tight, regular arrangement. So that's why your butter, lard, coconut oil, and palm oil are actually solids at room temperature. It's because they have a lot of single carbon-to-carbon bonds. Plants, though, a plant which is monounsaturated or polyunsaturated, when you have that double bond, one, remember that's a cis double bond, but these, when you have that double bond, it creates a bend. So now I think of these as being like forks, right? So for me, the only way I can make forks all line up in the drawer is I have to like put them in a row. But most of the time I just throw them in the drawer, and you know how they all stick up? So like, you know, they're half falling into the knife compartment because they don't fit unless you like set them in purposefully. Well, you don't put them in purposefully in terms of cells. So I drew kind of two. So see how they each have a bend? And so when they kind of go to fit together, they can't pack in tightly. This is why they tend to stay further apart, which keeps them liquid. So these are liquid at room temperature versus solid. So remember that saturated fats, animal fats, tend to be solid at room temperature because they have a lot of straight single bond carbon-to-carbon chains. The unsaturated, which are your plant oils, they can't pack in because the double bond creates a bend. And that bend inhibits them from packing in nice and tight. So they're kind of like forks in the drawer. They all sort of like do their own thing and they don't sit in nice and tight. And if you have the polyunsaturated, it's actually got an even bigger bend. So each one of those creates a bend. So you end up with one bend and then you end up with another bend. So you end up with this almost like U-shaped molecule with the polyunsaturated. That's the difference. That's why fats are solid. Like bacon grease is solid when it cools to room temperature. But if you cook in olive oil, the oil will still be liquid in the pan even after it's cooled. When you eat a fat or an oil, they're not typically single fatty acids. So digestion has to occur. And what digestion occurs, it's a hydrolysis reaction. So remember I told you hydrolysis is kind of when you break things. So fats and oils, they typically are ingested as what's called a triglyceride. Tri means 3. So a triglyceride, this is a molecule of 3 fatty acids. Can you see the long carbon chains coming off of this sort of center part? Can you see the zigzags, 3 zigzags coming off? Those are the 3 fatty acids. And they're actually, when you ingest a fat or an oil, they typically are ingested as a triglyceride. They're linked by that part that they've kind of circled in red. So this, that's called glycerol, which is where glyceride comes from. So that's really just like a linker. This is just what holds them together, this linker molecule. And notice in this one, this oil is actually polyunsaturated plus a monounsaturated plus a saturated fatty acid. There's all 3 of them in that one. That's why I said they're not all one type or the other. But in a hydrolysis reaction, you add water, and you see that you break this link. So the link is broken here, here, and here. So it like breaks the long carbon chain off of the linker molecule. So now I have 3 fatty acid chains that are formed. I have a polyunsaturated, a monounsaturated, and then a saturated one. So that's a hydrolysis reaction. Hydrolysis just uses water to break this bigger molecule into smaller ones. And then you can absorb these. I mean, you do have to have bile. You do have to like do some things to try and absorb it better because, you know, fats are not very soluble in water. But your blood is water, so that's a challenge. So you have to do some things to try and get fats into the blood and have it circulated and carried, transported from one place to another. But that's the hydrolysis reaction. So remember we talked about it before in the condensation versus hydrolysis.
Is it the 3 fatty acids because it's the 3 different zigzags?
Yeah, the 3 chains. Right? So when you eat, so this is really what you eat. So you don't typically eat an individual fatty acid. You usually eat a triglyceride. So when you have butter on your toast, you're eating triglycerides. If you have like a burger, you're eating triglycerides. Even if you put olive oil on your salad, you're still eating the They come in, they're ingested as a triglyceride. And then in digestion, you split them into their individual fatty acids. And now we can take these fatty acids and we can use them to build membranes. We can use them to build stuff like myelin. You can store these as fat, okay? So there's all those uses can come out of the building blocks, these 3 fatty acids that end up being formed. That happens in digestion, okay? So one of the challenges that they had in reactions is there was the challenge, or if you have butter, okay, so butter we know comes from cream, right? So it's you take the cream from the milk, and then you churn it to make butter. So there's some positives and some negatives. So butter, coming as an animal fat, we know that it has a much higher saturation, right? So these tend to have more saturated fatty acids. Butter has a pretty good flavor, okay? Not gonna lie, like if you put butter on a biscuit, like that's pretty delicious, okay? So butter in and of itself, flavor is high, it's used to increase sort of the texture of food as well as the flavor. But if you don't keep butter in the refrigerator, what happens? Has anybody ever had so I have a friend that grew up in France. And so when she was growing up, they never put butter in the refrigerator. Never. Butter sat on the counter all the time. Now, this was also because they ate butter every day. They had it with their bread every day. So like a stick of butter didn't last a whole long time at her house anyways. But if you let it sit out, it is a milk product. So what would happen if you left your milk out and didn't put it in the refrigerator? It'd spoil. Okay, it get kind of like sour tasting. Okay, if milk goes bad, like it gets all chunky and gross. Well, this is a milk product. Okay, it is cream where they have skimmed the cream, the high fat content out, but it still has some milk components in it. So if you don't keep it in the refrigerator and you let a week or more go by, it will go rancid. So it must be refrigerated. So otherwise, and if you go to the grocery store, pick up a pack of butter and look at its expiration date. Pick up a pack of margarine and look at its expiration date. Margarine's got a 9 months to a year expiration date. Butter usually is about 6 weeks. Okay? And if you've ever bought butter and you don't use it, it'll start getting funny, yellower over time. You open it and you're like, this is really yellow. Well, it's just because even in the refrigerator, kind of like it's a milk product, it does have a finite lifespan. So it doesn't last as long. So butter had a good, positive aspect. It's a solid normally at room temperature, right? So we like this. It's a solid. It's easy to put on toast. It's good to put on your baked potato and let it melt in, right? It's good on your food. It's got a good flavor. You got to refrigerate it. And it's got a sort of shorter shelf life. But then let's look at oils. Okay, so oil is extracted from a plant, most of them. Most of your oils, so we'll say that from the olive, from the corn, from the sunflower. So the seeds are pressed and the oil is collected. So flavor, what do you think these things taste like? So have you ever just gotten a drop of olive oil or a drop of vegetable oil? You made a face. Why? Because you think it tastes good? Not like butter. Flavor? Not as good. Would you take oil and put it on your toast compared to butter? Which would you rather have? Yeah, it's a liquid at room temperature. So it's not as spreadable. You can dip, but it's not as spreadable as butter is. What about lifespan? What about shelf life? A long time. How long have you had your bottle of vegetable oil in your cabinet? Think. More than a year? Probably, yeah. Couldn't do that with a stick of butter. You put a stick of butter on the shelf for a year, you'll have some friends living with you too, okay? But it's a long shelf life because it doesn't come from an animal product. There's no other like proteins. There's no other carbohydrates in it that you find in butter. So it doesn't have as good a flavor. It's not spreadable because it's an oil, but it has a really long shelf life. So then somebody said, okay, why can't we like merge these two? And this is where hydrogenation came in. So hydrogenation is where you take the unsaturated oil and you saturate it. You use a reaction to convert it into a solid. So here's how you do it. So we're going to take the double bond of the unsaturated. So remember that oils, these are the mono or poly. So they're either going to have one double bond or they're going to have multiple double bonds in the chain of the fatty acids. We're going to hydrogenate. That just means add hydrogen. And in doing so, we break the double bond and add a hydrogen to each of the carbons. So notice over here, there's two, like if this was H, 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 and H. These are still those 4 H's. But I'm going to add a hydrogen to each carbon, breaking the double bond, forming a single bond. So I'm going to take and change this from being an unsaturated oil to a saturated fat. Right? We said oils are liquid at room temperature, fats are solid. Typically, they need to add platinum, nickel, or palladium to it, and that should be above or below the arrow. So what is that? This really just should say this. This bothers me when the book does this. They put the H's above because if it's above or below the arrow, that's usually a sign that that is a what? Catalyst, right? So if you have just the arrow and you had like last week we had H2SO4 above the arrow in the reaction, remember catalysts don't get used up, but they speed the reaction up. So you can use platinum, nickel, or palladium as a catalyst to speed this reaction up, but there, hydrogen is a reactant. So hydrogen should be over on the left side. So in hydrogenation, we're going to take a liquid and we're going to form it into a solid by taking and breaking the double bond, forming all single carbon-to-carbon bonds. So there's the example. So if we look at this one, look at the top one, you see that out of the 3 fatty acid chains, 2 of them are unsaturated. The top one is a polyunsaturated, the middle one is a monounsaturated. So if I add hydrogen and a catalyst like platinum, typically you take in heat, okay? So you'll take this oil, take this liquid, you start to bubble hydrogen through over a platinum catalyst and you heat it. And the reaction will break the double bonds. Now, do you see in this bottom one, do you see that these are saturated? So if I made him all saturated, then I would end up with something that's as hard as butter. And so there is some complaint. Cold butter, have you ever tried to put that on your toast? What does it do to your toast? It just like tears it all to pieces, right? So you like take a cold stick of butter, a cold piece of butter, and you try to put it on your toast, and it like tears your toast all up. You're like, this butter's not melting. So they were like, instead of making it completely saturated, let's do a partially hydrogenation. So if we do a partial hydrogenation, we will add hydrogen to most of the double bonds, but not all of them. And that means that they'll be a little softer. So have you ever noticed that? Margarine is way softer than butter is, like even straight out of the refrigerator. So you know, like the I can't believe it's not butter, or the country crock that you get out, it's softer, and it is because there's a few double bonds in those fatty acids. They're not all saturated. That's why it stays softer, more like a little bit more like an oil, but it stays solid enough so that you can actually spread it. Now, if you take those out and leave them out on the counter, those will get really soft. So the tubs of butter or margarine, they'll get like really, really soft and mushy. It's almost hard to spread it. So during the 1950s, the hydrogenation of oil was used, and this is when margarine and Crisco came out on the market. So prior to this, the only options that you had is you could cook with butter, and you could cook with lard, or you could cook with oil. There were no other alternatives. So you had either oil that you fried stuff in, or you use lard, or you use butter when you made biscuits, right? So it was the 1950s. The big benefit in the ways that they advertised was now you have spreadable butter. And I would agree, margarine is softer, it's easier to spread. It has a much longer shelf life. It does, because it's not coming from dairy. It's not coming from milk. It's actually coming from an oil that had a long shelf life to begin with. This could actually be produced cheaper than it cost to keep cows. So you didn't have this reliance on a dairy cow to get milk to churn and make your butter. So that's why like margarine is cheaper. When I was a kid, margarine was like 25 cents for a pack of 4. It was like, I felt like they were giving it away. They said it's healthier because it's not an animal product. That was the other big kicker. It's healthier because it's not an animal product. Only animals make cholesterol. So lard and butter both contain cholesterol because they both come from animals. Lard comes from pigs, butter comes from cows. So because of that, there still was. And so this is like the 1960s when like the whole cholesterol thing, oh, cholesterol's bad. Like cholesterol's had a really bad rap for about 50 years, okay? But in this time, it was really pushed. Margarine and Crisco came on the market. So Crisco, the only way you could ever buy Crisco, now it's all fancy, but when I was a kid, Crisco came in like, we used to just get the big 3-pound tubs. Yeah, so the big blue tub, that's what you bought, was the big tub of Crisco, and that's what you used to make pie crust, that's what you used to make biscuits, that's what you would use. Yes, I know some people that use that still to make cookies. It's like, whoa. It like, makes me cringe. Huh? Yeah. Yeah, it's white. It's like a white solid, and it came in like a tub.
I used to use it to like grease my cake pans and cupcake pans.
Yeah, so you'd use it, because that was before they had Pam. So you would actually take and then you'd flour. Yeah, get a little Crisco and wipe all of your pans and stuff, and then knock some flour in, and then flour it, knock all the excess out, and that helped it to not stick as much. Yep.
Still the best way to make a German chocolate cake.
There you go. Okay, I don't have any arguments. All right, so, but this was their big claim. The problem and they said, here's what happens. We are taking a unsaturated, we're just going to break that double bond. We're taking this double bond, we're adding hydrogen, and in doing that, we're converting it to a saturated fatty acid. So everybody's like, all right, everybody jumped on the bandwagon. In fact, like sales of margarine, like exceeded butter. Okay, everybody had a tub of Crisco in their pantry. Okay, Smith and like all the oil producers are like, yes. Okay, problem comes in now. They said, well, wait a minute. If you have the double bond, if you have this unsaturated fat, if you're not careful, when you do hydrogenation, the majority of your sample will become a saturated fat, which is margarine. But a small percentage forms this. So go to the right. So most, like I'd say, like 99%. 99% of the molecules end up forming margarine. But about 1%, that doesn't even look like numbers, 99%, but about this, a small amount, that double bond breaks and reforms And when it reforms, it doesn't reform in the cis arrangement. Now it's what? Do you see how that is trans? Do you see the double bond looks like one thing sticking up and one thing sticking down? Do you see that that would still have that zigzag arrangement like the margarine has? So it would still pack in tightly? They said, that's fine, it's not a problem. Their big claim to fame, it's going to sit on your shelf much longer. In fact, they started to retool all the snack products. So way back when, like that was like the Hostess cakes, Twinkies, Ring Dings, okay, all of those. Then you had the Chips Ahoy cookies, Oreo cookies. These are like old school cookies, okay? The Nutter Butter. Not like the new stuff that they have now. Like these are old school cookies that have been around for a long time. Manufacturers actually switched to using margarine and Crisco in making their cookies and such because now we can make these, package them, ship them all the way across the country, and they're going to be able to sit on the grocery store shelves longer because they don't have butter. So convenience foods really picked up on the margarine and Crisco bandwagon because of this shelf life. So then, in the 1980s, people started saying, well, wait, trans fats. There are no naturally occurring trans fats. So nature doesn't make trans fats. So then the next question is, if nature doesn't make trans fats, how do we break it down? And the answer is, you don't. So when you take a trans fatty acid like that one up in the corner, that piece, like this little segment right here, that ends up hanging around. So then they started doing studies and said, you know, people that eat a lot of trans fats have a higher bad cholesterol number. They have more circulating fats. And the question always came back, well, how do we actually digest this? Interestingly, Europe actually banned trans fats in the 90s. They're like, nope, no more trans fats in our foods. The United States didn't get around to doing it until 2019. Took like 30 years. There was a lot of resistance because all of like the convenience food companies were like, we're going to have to redo all of our recipes. And then finally, it was supposed to be back in like 2013. They got an extension, then they got another extension. But in 2019, like they stopped giving extensions, and all of those they had to retool. So now a food product can be considered trans fat free if it has less than 0.5 gram of trans fats per serving. So it still can have some, but it has less than. Because these were all of the findings they found. If people were eating diets high in trans fats, they found that their cholesterol levels increased, which is weird because they're not eating animal fat, but it actually increased their cholesterol. It increased what they call circulating triglycerides, just the amount of fat in the blood. And that increased the formation of plaque and led to heart disease. So there was like direct correlations of heart disease related to the amount of trans fats, but it still took almost 30 years for the United States to actually get rid of it. So then some people are like, well, what are you talking about? What kind of foods? So maybe it'll zoom, maybe it won't. Okay, no. So looking and thinking about those, what have you had in the last month? Microwave popcorn, I have. Pizza, frozen pizza. I haven't had any frozen pizza, sorry. Anything else? There's biscuits, like the biscuits in the roll. We used to eat those all the time when my kids were little. I don't eat them anymore, but that was just because, like, you got to feed them something. Jeez. And you got to feed them fast. What else? So, like cookies, cakes, like those graham cracker pie crusts, even like prepared frosting. Okay, so you know, like the frosting in a can. Okay, so all of these still have small amounts. They used to have a lot more. All of these, in fact, some people complained that Oreo cookies did not taste the same. So when they went to the trans fats, like the no trans fat recipe, people were complaining and calling Nabisco going, what is wrong with these cookies? They don't taste near as good as they used to. Well, that's why. Well, man, we had to take the trans fat out. They didn't like that. So your diet now has lower. There's still only one source. Unfortunately, if you take an oil and you heat it at a high temperature for a prolonged period of time, you can still, just the heat, not even adding a catalyst, but the heat of that oil can actually cause hydrogenation reactions to occur. So what food can you think of that you eat that has been in oil that has stayed hot for a long period of time? It's probably not at home. So stir-fried food. The only thing that's good about stir-fried food is it's not heated for hours. Has anybody ever worked at McDonald's? Anybody? They turn the fryer on when? All day long. Yep, the ones that are open 24 hours, they never turn their fryers off. So they found that if you take and heat an oil for 10 plus hours, the heat of that cooking oil will actually convert it and cause partial hydrogenation. So like your French fries, your Chick-fil-A, anything that's fried. And that, like the government's like, well, we can't do anything unless we said no more fried foods for none of you. Then there would be riots. It wouldn't work. Huh? Yeah, that's like they couldn't buy their way out of that. But
is that why you can taste the difference in the fries after they do an oil change?
yeah, well, and I don't know how long, I've done some research reading, they've actually taken oils and kept an oil at 160 degrees Celsius for 1 hour, 2 hours, 3 hours, 5 hours, all the way up to 10 hours, and measured the amount of trans fats that were produced over that time. And they really saw past 10 hours, that's when they started to see more and more trans fats formed. And it's all just because of heat. The heat is basically breaking that double bond. But then 99% ends up being saturated, but a 1% form of that trans fat exists. And so, but then again, you also think about other countries other than us. They're not big fried food eating countries. I mean, those people eat a lot of cream and a lot of butter and everything else, but they don't have the fast food type of thing. It's just not nearly as common in other countries as it is in the United States. So that's really now, that for us is really the big thing, is your ingestion of fried, commercially fried. They've shown if you do it at home, it doesn't happen because you put fresh oil in, you heat it, you cook, you're done. Your chicken is cooked in 30 minutes, right? It's that oil doesn't stay hot for 10 hours. So that's where they see that there's still some trans fats that are formed. Yeah, but so home frying it, you're not going to be heating that oil as long as McDonald's is. The places that keep the fryers hot all day, then that's 10 hours, that oil's just under smoking temperature. It stays super hot that time. Because that's speed then, right? So you dump your chicken in, you dump your fries in, your onion rings, whatever. I mean, I'm not going to say that I don't eat any of that stuff, but I'm just saying that that's now in our diet, that is now the most prevalent form of trans fats that we're ingesting because of the ban, because they finally kicked out almost all the convenience foods. And it was terrible because that was pretty much trans fats was in everything that's prepackaged, pre-made, convenience food type of stuff. So I was like, geez, they're really targeting people. People that don't really have the time or the money to go get something and make something from scratch. Okay, last one, or do we have time? 7 o'clock, I have to stop. You didn't stop me. I'm just telling you a story, that's why. Okay, so the last one that we'll talk about, so on Wednesday, hydration is the last topic for chapter 5. Okay, and then we can go on to carbohydrates.